It was easy for our ancestors to figure out that every year, one day had the fewest hours of daylight and one day had the most. And these made an easy way to divide the year in half. And since we love organizing things, we divided it again, marking days halfway between the two. The equinoxes, the day when there's equal day and night. Except day and night on the equinoxes isn't equal. And they're not halfway between the shortest and longest days of the year. The equinox probably isn't what you think it is. Instead of being a whole day, the equinox is one very specific moment. When Earth's axis isn't pointing toward or away from the sun at all, which is also when the center of the sun crosses the equator. But if exactly half of Earth is bathed in darkness and the equator is perpendicular to the sun, then why doesn't the equinox have equal day and night? Because we mark sunrise when the top of the sun rises above the horizon and sunset doesn't happen till the last sliver disappears, day is several minutes longer than night on the date of the equinox. If the sun were a point instead of a disk, this wouldn't be a problem. But even then, the sun would appear to be up in the sky for longer, because near the Earth's horizon, Earth's atmosphere acts like a lens, bending the sun's rays to make them visible even when it's already dropped below. As a result, the date when day and night are exactly equal, the equilux, happens a few days earlier than the equinox in March, and a few days later in September, although precisely when depends on your latitude.
Acts like a lens, depends on your latitude. As a result, then why?
And I'm like, dude, nobody is disputing the idea that refraction exists. What we're disputing is, first of all, the fact that you are doing your math and your calculations based on a flat Earth. And it's not a flat Earth, because when you start getting away from that point of origin, the atmosphere gets thinner and thinner and thinner. And I said, and I also find it ironic that the demonstrations that Mick sent me, that you sent me, Mick, were little refraction demonstrations on a flat surface. It's like, what's the matter? Can't you do it on a convex surface? Can't you give us something like we would actually see, if the Earth was curved?
Earth's atmosphere acts like a lens, even when it's already dropped below.
He tries to minimalize it. It's like, yeah, we mentioned a lot of reasons in the video why 7.6R or standard refractions is BS, right?
Yeah.
But he never, of course, not once does he ever address the fact that, as you go away from that target, that the Earth is dropping away from that laser beam, and therefore, it demands then that the atmosphere becomes thinner and thinner and thinner the further that you look out. And that is exactly the opposite of what they're saying, when they say that the refraction's happening because you're looking through this ever-increasing dense atmosphere. Now, in a flat Earth model, that's absolutely true. But it totally changes the game when you put it on a ball. So
as a result,
when you see, for example, this situation, you must be assumed, because when you see in real time, and you can see this is from 263 kilometers, you see the sun, assume we are on the ball Earth, you see the sun setting down. So in what time this situation becomes? Because when you see this, you see the sun come from up to down. So at what moment this, transition happen? When you start to see the mirage, when it start happen the mirage, when supposedly right now the sun is down, but 2 seconds early the sun was up. Because if we assume this situation, we must believe that the sun start to invert his position, like right here, at the beginning of all this video, because there is a lot of examples of this. So just I mean, right now, the sun must be at this position here.
As a result,
The fact is that the light will only bend as it goes into a denser medium, and that will bend it down or one direction only, however you want to look at that. And so this is what I was referring to essentially, is that
But if that's a
So it would self-correct and return to normal when you approach the less dense medium. Is kind of what I see what you mean. Yeah.
right, only with respect to where it was before.
when you look at like Soundly's little test where he does the 7 lights and we see all the refraction up and down, well, we actually don't see refraction up. We only see it bend down, and then it comes up to level, and then it goes down and it goes straight, and they just keep pausing the camera when it's bending. Well, that bending is not reality. You're just seeing the bending from refraction. The reality is the straight line.
Right. So when Globers see a ship going off in the horizon, they assume that the light's going in perfectly straight lines, because that's, assumed when it's convenient for them, of course, but only then. So you assume that light's going in straight lines and that the ship's going down a curve in the distance. But what's actually happening is the ship is going across a plane, and perspective applies. But the inbound light is also not going in a straight line at all. It's going to refract or bend down towards the ground level. And so it's the light that's curving around the plane Earth, not the spherical Earth that's curving underneath perfectly parallel straight light.
Correct. And we know this because there's nothing that can be lifted up over the water and displayed for you, like buildings and things like that.
as a result,
You can clearly see how the image of the sun begins to going down. You can see the deformation. So at this particular situation, all the indications from the atmosphere is that the image was going down, not going up, because you can clearly see how the distortion of the supposedly everyone knows that the sun is a perfect disk. So here you can see how the lights start to deforming and pulling down.
The sun's rays to make them visible depends on your latitude, even when it's already dropped below.
It's like, what's the matter? Can't you do it on a convex surface? Can't you give us something like we would actually see, if the Earth was curved?
First, I'm going to show a part of Mr. What's the word when somebody oblivious? Mr. Oblivious Wolfie 6020. That's him there, Wolfie 6020. Utterly, completely oblivious of the fact that not only has the equinox been sun-tracked over a 24-hour period, more than once by flat earthers, never by globe earthers, but that's embarrassing only for Wolfie 6020, who doesn't seem to know that. Okay, so I pointed it out to him in a comment here. Okay, it's been covered, but he shows this countdown. I'm going to play his video, and then you'll see why this is embarrassing for globe earthers, Dr. Donners, and Xenoskeptic, especially for you two. So pay attention to what he says.
This is the countdown timer to the September equinox. As you can see, we have 12 days remaining. This will be the 5th equinox to occur since I encountered Flat Earth on YouTube in August 2016. And on each occasion, I have encouraged flat earthers to go out and make actual observations of the sun angles on the equinox. For some reason, they continue to remain reluctant to do so.
Maybe change that to, for some reason I'm saying this despite them having already done that.
And personally, I find that quite puzzling.
It must be puzzling. Like in the real world, it's been done by flat earthers. But in the real world, you think it hasn't been done by flat earthers. Oh, that's embarrassing. Speaks of like early onset Alzheimer's, perhaps. But let's wind on. Oh, this is precious. This is absolutely brilliant. So he goes on to say equinox, so on and so forth, on this date. Like, oh, on this date, the one shown on the screen. But the one that I was showing at the start of this hangout. So let's go to here, okay? And listen, this is the Kisato equatorial sundial, even though that's not an equatorial sundial. Just, you know, thought I'd point that out. That's a sundial. It's not an equatorial sundial. An equatorial sundial is on an arc. I'll show one, okay? But let's carry on listening to him.
To understand this experiment, we're first going to look at the Quixote sundial, which is located directly on the equator near Quito in Ecuador. So as you can see by the people on the sundial, it is quite large, and because it is located at the equator, the gnomon is vertical.
Ooh.
Because of its design.
The gnomon can be vertical anywhere on Earth.
The shadow projected by the gnomon on the dial lines can indicate solstices, equinoxes, and also months of the year with great precision. Because we are talking about the equinox, we're going to focus specifically on the line representing the path of the shadow on the equinox. So the line that we're interested in is this one, which runs directly through the center of the sundial, passing through the gnomon, and the orientation is directly east and west.
Okay. Let's just let's go to Google Earth. See that sundial, shall we? Bear with me. Here we have Google Earth. You might notice, see this yellow line denoting, well, it says there in yellow, equator. This yellow line, you know the yellow line that is on the bottom edge here of this line? And you see how that line veers off? It's like, good Lord, it veers off. Can you see how it veers off? Can you see how it veers off? It's like, good Lord, what's happening there? Maybe rotate this around a bit. Oh no, see what happens? Because like when you rotate this around, like that line is still veering off. Oh, so it's not quite east to west, is it, Wolfie? Oh dear. Okay, so that is not actually east to west. It's east to vaguely west. Okay, but it's not 180 degrees. Okay, now let's stop screen sharing that. Oh God, this is so embarrassing to have to address this to globe earthers. It's embarrassing. It really is embarrassing. So he thinks it goes east to west. Oh dear, he didn't even bother checking. He went to Wikipedia, saw a diagram of it, and thought, oh, there you go. Okay, so let's move on to this. Gonna refresh. Oh, don't need to refresh. This is counting the time to the equinox. It says here, time until Saturday, 22nd September 2018 at 21:54 New York time. That's when the equinox starts.
One very specific moment.
Okay. Apparently, okay, according to this front page of Time and Date. Now we have to remember, just like NASA, just like anybody else working for the globe, there will be facets of their organizations that are there to address the lowest common denominator, the half-wits who don't bother checking things and wouldn't know what they were looking at if they did check. And then they have the real details for people who want to actually take notes or make plans, you know, that kind of thing. Okay. So this is the September 22nd, not the 24th, the 22nd at 21:54, New York. New York, this goes for the globe links out there, is on the Western Hemisphere. If you take your ball Earth and you split it vertically from pole to pole along the Greenwich Mean Time, it comes out at the International Dateline. And now you have in your hands a left hemisphere and a right hemisphere, and the left hemisphere is your western hemisphere. Okay, that's why, like, the West is like America, that region, even though on the other side there's a portion of Russia too. But never mind that. Okay, and New Zealand, where Wolfie is on the eastern hemisphere. So there might be a bit of confusion there. We'll clarify that. Okay. So time and date. When it is in New York, the time set, I've set it to 21:55 instead of 21:54, simply because you can't set it to exact minutes on time and date. Okay, not on this time translation. So that means the equinox starts at 1:55 in New Zealand, in Auckland. I'm not sure where he is, but I'm just going by Auckland. Okay, so that will be Sunday the 23rd of September. Okay, at 01:55 UK time. Okay, now let's check. This is Auckland, New Zealand, 23rd of September. So it's all fine up to now, Globelings, don't worry. 23rd of September. Sunrise, we're going to pay attention here to where it says azimuth. Here, where it says azimuth. Okay, azimuth. 90 degrees at the bottom here, 90 degrees, 0.59. We'll forgive the point anything, okay, as long as it's 90 and 270. So sunrise at 90:59. Okay, let's forget the 59 again. Okay, and sunset at, oh dear, 269, but we'll forgive that too. We'll pretend it's 270. Okay. You might note that sunrise starts before the equinox starts. The equinox starts at 1:55 New Zealand time, 1:55 p.m. New Zealand time, but it starts a bit ahead of time. Let's pretend that's not important. Okay, let's go to Edinburgh. Now we're on the Western Hemisphere. Okay, so we'll go from Edinburgh and Ushuaia, also on the Western Hemisphere. Okay, and the reason I chose Ushuaia and Edinburgh is that they have approximate distances from the equator. That's the point where the sun is casting its light directly 90 degrees overhead, the equator, that thing. So Edinburgh is 55 degrees north, Ushuaia is 54 degrees south, both on the Western Hemisphere. Okay, so on the 24th of September, goodness gracious, that's the 24th, not the 22nd. Can you see? I'm highlighting it here. That's the 24th. Look, 24th of September.
The day one day had one very specific moment.
Oh, that's embarrassing, isn't it? That's not the 23rd, it's the 24th. Oh, it's also not the 22nd. Let's see what it says here. Oh, it starts on the 22nd of September. So you think maybe the next day, the 23rd of September, but no. The 24th. In Edinburgh, on the 24th of September, sunrise will happen at 89.45. According to this, we will check with time and date, okay? And sunset happens, oh, sorry, that's culmination, silly me, at 2:70. That's great. We'll call that the equinox in Edinburgh on the 24th, not the 22nd or the 23rd, but the 24th of September. Let's check, just double check with time and date. There's a couple of minutes difference here and there, and half a degree or 1 degree difference here and there too. So we're on September, and we're at Edinburgh, September 2018, sun in Edinburgh. We're at the 24th, and you can see here, these columns in bold, they tell you the degrees of elevation, the azimuth, for sunrise and sunset. So 24th, sunrise at 90 degrees, that's east, and sunset at 270. 25th, sunrise at 90 degrees and sunset at 269. So we'll go with the 24th. Okay? Are you paying attention, Globelings?
One very specific moment, you can clearly see how the image of the sun begins to going down, even when it's already dropped below. Depends on your latitude.
Supposedly, right now the sun is down, but 2 seconds early the sun was up. You know, because if we assume this situation, we must believe that the sun start to invert his position. You know, like right here. You know, at the beginning of all this video, because there is a lot of examples of this. So, just, I mean, right now the sun must be at this position here.
The sun must be at this position here. So at what moment this, transition happened?
This is 2 days after the equinox starts. This is the 24th. Equinox starts on the 22nd. Let's say it's just 1 day different. Okay, 22nd, Western Hemisphere, 55 degrees north. Now let's check Ushuaia, Tierra del Fuego. Okay, and sunrise, 90 degrees. You see here, 90 degrees. And sunset, 269, close enough. We'll call that 270. Oh, wait a minute. It says the 21st of September here. What's going on? That's the 21st of September. That's the day before the equinox starts. It's on the Western Hemisphere. That's peculiar. Let's double check with time and date. 21st of September, sun rises at 90 degrees, sun sets at 270 degrees in Ushuaia, 2018. Did you see that? This is on the 21st. This is 54 degrees south on the 21st. 55 degrees north on the 24th. I'll let that sink in. Okay, do we got that, Globelings? Let's go over it again, just in case you've only just started watching. So, Wolfie6020 says at the beginning of his video, I'm paraphrasing for comedic effect, I can't believe flat earthers haven't done any tracking of the sun on an equinox. We have. We've done it at least twice that I know of. And your friendly neighborhood flat earther pointed that out to him here. Okay? We've also done it on the solstices. Oh dear. But never mind that. Now, he says, oh, silly flat earthers, for some reason, even though I offered to give out prizes to any Globelink who offers to, agree with what I'm saying, somehow flat earthers aren't doing this checking of the sun. And he shows this being at the equator. I've shown this at the equator on Google Earth, not actually being very east to west, not 90 and 270, just a little bit off, a little, like people can't check with line of sight, but it's a little bit off. Wolfie didn't actually bother checking. I will check in a minute. I haven't already checked to see when it happens in Quito, the equinox. But I then went down to this, which tells you when the equinox starts, okay? And then I checked when that is from when seen from New Zealand, because he's in New Zealand. So I checked, and that is 1:55 p.m. I then checked when the equinox happens in New Zealand, and it happens on the correct day, which is the next day, the 23rd, instead of the 22nd. Unfortunately, the equinox hasn't started yet and won't start until, well, watch me scroll this. I'm scrolling this. That's when the equinox will start, apparently, okay, time-wise, okay? But never mind, here, it starts already on the 23rd. Brilliant. People in New Zealand can go and check the equinox. Excellent. And they can all think, oh, isn't it strange? It happens everywhere in the world at the same time. And then I've shown with both SunCalc and time and date that it doesn't happen in the Earth on the same day at the same time at all. It happens with like 3 or 4 days discrepancy at least. And that's with just the few that I've checked. So I showed this. I went to Edinburgh, which is, I'll show you here. Look at the bottom where I'm scrolling here. It says height 70 meters off sea level, okay? And it says latitude 55 degrees north. And then I checked with Ushuaia, can you see, which is 54 degrees south. Pretty similar distances from the equinox. And this is when, from the equator, and this is when the equinox is supposed to happen. But strangely, in Ushuaia, the equinox happens on the 21st of September, and in Edinburgh, the equinox happens on the 24th of September. Can you count with your fingers? Okay, so now just, oh, and then I verified with time and date. Here's Edinburgh. See, look, Edinburgh, and anybody can check this, including Wolfie 6020. Okay, Edinburgh 24th, sunrise 90 degrees, sunset to 70 degrees. And then Ushuaia on the 21st. Remember, Ushuaia is on the same day, you know, hemisphere speaking, is the same day as Edinburgh. In fact, it's only a few hours after Edinburgh. But somehow, on that day, they've had it already 3 days before. So, 21st, Ushuaia. Ushuaia, 21st. Look, Ushuaia, sun in Ushuaia. Now what I'm going to do is I'm going to check, just for the hell of it, in Quito. Just let's see. Now, in the mind of the Globelink, what will be happening right now is they will be scrabbling for reasons how that could be so. Why? Why it could be so. Like, it must be, okay. So I've just gone to Quito, Ecuador, okay? And I haven't changed the date or anything. It's already telling me that at sunrise, It's at 90 degrees. Looks like equinoxy, pretty equinoxy. Okay, remember Quito is in South America, and so is Ushuaia. Okay, so don't get confused like that. Okay, so sunrise 90 degrees and sunset 269. We said that we would allow a little bit of flexibility. Call that the equinox. Just to check, we'll go to the day before. Let's see if the day before has a closer equinox. So sunrise, oh, it might be 90, and sunset 269. Not really. Let's go to the day before. That's the 22nd. And sunrise 89, and sunset, oh, now it's 270. Okay, maybe it's some kind of rendering thing for this, for this program. It might be a bit buggy. So let's check on time and date. Let's just see when it happens in the real world, because like I said before, time and date do show real details. From time to time there are aberrations, and they don't show the aberrations. You have to be there looking yourself, say from Cape Town. But anyway, I'm going to Quito, Ecuador, and September already. Let's check what day it rises at 90 degrees and sets at 270. Oh, look here on the 23rd. You might notice it's not the 22nd, it's the 23rd. Okay, and let's remember, in Ushuaia, it's on the 21st, and in and all of these on the Western Hemisphere, and Edinburgh is on the 24th. And like I said before, Globelings, look, can you count? Let me help you. We'll not count the one that we're on already. We'll count after. So 1, 2, 3. Can you see? I just counted 3 days difference. What else could I do? How else could I check? A thing to do would be to maybe check the time difference. Let me see. Somewhere I had it already. Here. And we will check New York, and instead of New Zealand, we will check Ecuador. Let's see time difference, just in case there's some bizarre thing going there. Don't think so. I think Ecuador is pretty close to the same time. But let's see. Ecuador, Quito. Here we go. Let's see. 22nd. So yeah, see, pretty close. 1 hour difference. Okay. So equinox starts at this time, which is this time, on the 22nd. Okay. And let me see where I had it. Here's Quito. And let me see, was it here? I might have lost my page. 1 second. And here's Ushuaia, sorry. And yes, I think I lost a page. I will just go back. Okay. So same time frame. I mean, it's only less than 15 degrees difference. If you want to look at it that way, you know, don't get confused though, or maybe get confused. Maybe start clinging to degrees and say that it's a fault of degrees. Remember, this is the equinox we're talking about, 22nd of September, and we just saw, where was it, that it happens on the 22nd of September. Okay, and let me go back. Just go back here. Oh no, this is Ushuaia, where it happens on the 21st. Let's go back here. No. Let's go. Apologies for the oh, here. So on calculator, go back to Quito. Isn't this embarrassing? Isn't it embarrassing having to explain this 22nd to globe believers. See, 22nd, equinox. 22nd, equinox, Ecuador. Brilliant. Now I'm going to show on this little map here. You see Ecuador here, okay, 22nd. Ushuaia is here, just slightly east of it. Okay, can you see? Does the equinox happen in Ushuaia on the 22nd? No, maybe it has to rotate round and then have the equinox. So maybe the equinox happens on the 23rd. Well, no, actually, the equinox happened the day before on the 21st.
Then why
Somehow, Edinburgh doesn't happen till the 24th. So now I'm going to go to the comments in the chat and I'm going to ask specifically for Globelings to explain. Oh, wait, Bob Johnson writes a comment. The sunrise is due east in London on September 22nd, but on fuck math, it's over the equator and not part the further map is the equator due east of London. Okay. I just showed how in Edinburgh it was on September 24th. I've looked at my own location, it's September 24th. I haven't actually looked at London. I might go and look at London now and see whether or not you're being honest. In fact, I will do it right now whilst I'm chatting to you guys. London, UK, and see whether it's the 22nd or the 21st or the 24th or I don't know. Let's see. So I'm going to the 24th. I'm just checking myself, guys. I'm not screen sharing right now. 24th rises, on the 24th it rises 89.57. So we said we'll give them a little bit of flexibility and it sets at 269. Okay, let's go to the 23rd. And this is London, okay? 88. Oh, and 270. Not east and west. Now let's go to 25th, let's say. Now it's 90 for rising. This is on the 25th. I tell you what, guys, I will screen share so you can see. So, right. And share again. Where is it? Yes, here. Okay. So, and then I will check time and date. Okay. So London, UK, 25th of September. Sunrise at 90 degrees east and set, well, at 269. Goodness gracious, it looks like kind of 25th for the equinox in London. But wait, if we go to the 24th and we look at the sunset, sunset is at 269 again, but the sunrise is at 89. Okay. Well, let's see what happens on the 26th. Let's see. Sunrise at 90.78 and sunset at 268. No, looks like 25th is the closest to equinox that London will have. Are you hearing this, Flat Earth Math, Charles? 25th of September, London. Sunrise at 90 degrees east and sunset at 269.33. That's London. Let's go to the 23rd. Sorry, that's the 25th. Let's go to the 24th. Sunrise at 89 and sunset at 269. Okay. Let's go to 23rd. Sunrise at 88. And we know how the the illumination moves southwards, so we know. 25th, so London 25th. I should have checked that, shouldn't I? But to be fair, I wanted to find something that had similar distance from the equator in terms of latitude. Although this makes a very good one, doesn't it? London, 25th. Stockport, 24th. Oh my gosh. So 24th, okay, let's say 24th. This is a slightly different time and date. So on the 24th, it rises at 90 degrees, and 25th, it rises at 90 degrees, but 24th, it sets at 270, and 25th, it sets at 269. So we'll say 24th for the eclipse. Okay, you can relax a little bit, Globelings. Now, just pause this a second. Dan Winfield, Dan W, please time out the lying cretin Bob Johnson who's still saying the eclipse happens on the 22nd in London. I've just shown that it doesn't. So please just say, yeah, same as freaking arse. The fact that the equinox does not happen as the globe model predicts breaks the globe model. Now, some flat earthers might not understand this. Some definitely will. For sure, globe earthers don't understand it at all. But we'll look at it. Okay, so here's flat earth math. Hello, Antonio. You keep using the word equinox with your own personal definition. No, I don't. For the rest of the world, it is defined as when the sun crosses the equator. This happens at one moment in time for the whole planet every 6 months. In theory, if we were in a globe, that would be the case. Now, listen to this. I'm going to play this several times.
Now I'm going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we well, don't laugh, that's really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature, or we say compare to experiment or experience. Compare it directly with observation to see if it works.
Now, that's a critical part in this. Compare it with, listen, so you compute, you calculate what that would mean if the theory was correct, what it would mean, what it would imply. Listen, he says it very clearly, okay? So
then we well, don't laugh, that's really true. Then we compute the consequences of the...
So we compute the consequences. If that was the case, then what would happen? Okay?
To see what, if this is right, if this law that we guessed is right, we see what it would imply, and then we compare those computation results to nature.
We compare to nature.
Or we say compare to experiment or experience. Compare it directly with observation to see if it works.
That's a key thing. See, so experiments is just one way to test if there's no natural way other than experiments, like looking at nature, for instance. So it's experiments and or nature and or observations, which are obviously of nature or of the experiments. Okay?
If it disagrees with experiment,
if it disagrees with observation of nature or with observation of the experiment, if it disagrees with empirical evidence, not just experiment, okay? For the globe-minded there, don't be fixated on the word experiment. You heard him say experiment, followed by or, okay? So compare it with nature or experiments or. It's those things are bound together. Make a Venn diagram and put them all in there, okay?
It's wrong.
If it disagrees with experiment, experience of the natural world, it's wrong.
In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all.
That's right. Now, I'm going to rewind it because I will be playing it again. Now, remember where Flat Earth Math said, this happens at one moment in time for the whole planet every 6 months. Okay. He then goes on, it is not defined as 12 hours of sunshine and never has been. The equinox is not defined as 12 hours of sunshine and never has been. Now, given that he's accusing me of having this own personal definition of equinox, and that he clarifies what equinox is and what equinox is not. It is not defined as 12 hours of sunshine and never has been. Cheers. Okay. Maybe he should contact National Geographic, see what they say. I will read this. Equinoxes are moments when day and night are of equal length. Look, it says day, 12 hours, night, 12 hours. Now we'll go back to this. It is not defined as 12 hours of sunshine. Let's go back here. Play. Oh, 12 hours, 12 hours. Equinoxes are moments when day and night are of equal length. Oh, sorry, I forgot to do the stupid voice. They occur twice a year on every planet of the solar system. Equinoxes happen when the sun is exactly above the planet's equator. This causes the terminator, or dividing line between daytime and nighttime areas, to pass through the planet's north and south poles. This unique angle causes every area of the planet to experience approximately the same amount of daylight and darkness for 1 day 2 times each year. Don't worry, this is a kicker, by the way. And then description of vernal and autumnal equinox and the orientation of the Earth and theory, which Feynman would say, no, it's wrong.
Oh, look at him laughing at himself like he's some kind of genius. Should we tell him that the autumnal equinox this year is the 23rd?
Is it?
Tell him it's the 23rd next year too? Okay.
One very specific moment.
Hey, genius, the autumnal equinox this year is the 23rd.
No, they said, not according to your own theory anyway. You got that wrong. But now let's go to this. So we'll go back to what Flat Earth Math was saying. You see, he's seen that there's a problem when looking at the equinox from 90 east to 270 west on the azimuth. He's seen this, and he's trying to like corral the minds of the globe earthers into thinking of it in some other way. And he actually states it is not defined as 12 hours of sunshine and never has been. Wrong. It's supposed to be 12 hours of sunshine because it rises at 90 east and sets at 270 west. That's what your equinox is supposed to be. Both. Okay, so now we're going to look at Jakarta. So first we look at the 270, okay, 90 and 270. So look, on the 22nd, here, rises at 90 and sets at 270. On the 23rd, it rises at 90 and sets at 270. Remember where he said 1 moment in time? Wow, that moment in time lasts like 24 hours in Jakarta. And you might think, that's a bit specific. Well, it isn't to people in Jakarta. So 22nd and 23rd, see these two. But wait, we just saw that, oops, these guys defined it as here, 12 hours of day and 12 of night. This is National Geographic, okay? 12 hours of day and 12 hours of night. So let's go to Jakarta and see when, we're going to look at this day length, the next column here, okay, like these numbers. And we're going to look at when it is 12 here, when it says 12, okay? So is it the 18th? No. Is it the 13th? No. Is it the 9th? No. Getting closer though. Oh, look, the 6th. Well, no, not the 6th. Oh, the 3rd. The 3rd is 12 hours. Goodness gracious, that's 20 days away from the 23rd. Look, this is time and date again. See, Jakarta. When is it 12 hours of day and 12 hours of night? Well, about 20 days before the 90 East and 270 West thing. Okay, so let's just clarify. This says the equinoxes happen like this, based on duration of day and night. When we look at duration of day and night, we have entirely disparate days, all kinds of different days. Here it's the 3rd. Let's look at where I am. I'm in Stockport, okay? Let's see when in Stockport it will be the equal night. So Stockport. You can go and do this at home, and I mean, if you're at home, you can just do it without going anywhere. Just visit time and date. So let's see, when will it be 12 hours in Stockport? Ooh, the closest is the 25th. The 25th is the closest in Stockport. Let's just pick a place at random. Washington. There, I just don't know why. I just thought of Washington. Okay, so Washington DC. Washington DC. There. Let's see. I haven't looked, so it might be the same day. Let's see. When will it be 12 hours? Okay, we're looking on this column. So the third one along. Oh, that's peculiar. It looks like wow, and I really hadn't looked earlier. It looks like Washington DC doesn't have an equinox at all. Let's see, 12 hours and 1 minute and 44 seconds. Let's go earlier. Maybe they have it much earlier in the month. Maybe. No. No equinox in Washington DC. Let's check in Buenos Aires. Let's see where Irulanducci lives. And again, I haven't checked these. I'd only checked Jakarta, and that's thanks to a subscriber who pointed it out in a comment. He's like, thank you. So we're looking in Buenos Aires. Let's see. We're looking at, again on the third column for when it's 12 hours. Oh, there. On the 18th, it's just over. We'll forgive those 32 seconds, okay? On the, 19th. It's interesting. Let's check Birmingham. 12 hours. Ooh, on the 25th, similar to Stockport, okay? It's just a little bit over. We'll forgive that. So, it turns out it's not a moment in time. Silly boob. It's not one moment in time for the whole planet. And it turns out that it is defined, like literally defined as 12 hours of sunshine. Like literally, it is defined as 12 hours of sunshine and always has been. You see, the word equinox means equal night. And you can't have like a 13-hour night and an 11-hour day and that be equal. See how that goes? So what do I have here? Now, just to compare, because there would be globelings who are the brains, the gears would be like grinding, looking for excuses, like reasons for it. So now we're going to play yesterday's video, Equinox punchline, flat Earth, and I'm just going to play it because it is the same longitude for the two places, and it is the same distance away from the equator for the two places. So I'm just going to play it all of the way through, and then I will stop screen sharing so I can see what's going on in the chat.
Ushuaia, Canyapiscau. Ushuaia, Canyapiscau. Ushuaia,
This was checking the 90 degrees sunrise and 270 sunset, not the 12 hours of day.
Ushuaia,
21st of September.
Canyapiscau.
Remember, this is not the actual equinox. This is just the rising at 90 and setting at 270. And that's 24th in Canyapiscau. And now I show on Google Earth, or the Rubik's Earth, as I like to call it. See that red line? That's the longitude on which they both sit.
Ushuaia.
And Ushuaia is at the bottom.
Canyapiscau
is at the top. And now I'm scrolling through the days to see when the 90 degrees, and that's regarding Wolfie's gaff. Okay, now is the equinox, well, sorry, the 90 degrees rise and 270 set. And a day has gone by. And it's still not in Canyapiscau. And another day has gone by and still not in Canyapiscau. And another day goes by and it's still not in Canyapiscau. Flat Earth math looks like your one moment is going very, very wrong. Now is the end of the equinox. So now let me stop screen sharing. Oh, wait.
Don't let anyone misinform you. The truth is out there. You just have to find it.
Ooh.
Thanks for watching.
Yes, thanks for watching. Now, I'm going to go back to this. Remember what Flat Earth Math said and how that's literally wrong in various different ways. First, I was not using the word equinox with my own personal definition. I was simply showing how the idea that it rises 90 east and sets 270 west is wrong, that it happens on a given day, that's just wrong. And then he goes on to say that it is not 12 hours of sunshine. Yes, it is, and it always has been. Okay, but then he goes on to this. It happens at one moment in time. Well, we've just seen it definitely is not one moment in time. Like, definitely is not. And then we saw, the definition and explanation of the equinox according to National Geographic. Didn't actually mention 90 east and 270 west. You know, I just thought I'd point that out. But it did mention 12 hours of day and 12 hours of night, given that that is what the equinox is supposed to be.
One very specific moment.
Going to discuss how we would look for a new law. In general, we look for a new law by the following process. First, we guess it. Then we come. Don't let.
And by the way, this is not when they're looking for a new law. This is when they're looking for a theory, a solid theory, not a law, okay, a theory.
But really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guessed is right, we see what it would imply.
So if the theory was right, we see what it would imply. If the Earth was a globe with latitudes and longitudes and places situated as the globe believers believe, then they would calculate what it implies, and it implies that at one point of the year the axis is in such a orientation to the sun that the sun is directly above the equator, and everywhere on Earth has the sun rising at 90 degrees and setting at 270, and everywhere on Earth has a 12-hour day and 12-hour night. Turns out none of those things happen. Not everywhere has 90 and 270 at all. And not everywhere, definitely, has a 12-hour day and night on that same day as when it is 90 and 270. Like, just totally not at all. So how do we test to see if the theory is right?
And then we compare those computation results to nature.
Nature. We compare with nature. The globe says this is what should happen. Let's see if nature agrees. Oh, turns out nature doesn't agree.
Say compared to experiment or experience.
See, experiment or experience. See, the experiment is there so people can experience the results of the experiment. You know, if you can't, you know, do something to scale, then you might, we all understand.
Compare it directly with observation to see if it works.
So compare it directly with observation. So compare the theory with observation, either observation of an experiment or the natural world. It's not hard to grasp.
If it disagrees with experiment
or observation of the natural world,
it's wrong. In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
That's all there is to it. It really is that simple.
So we have to go another day ahead to the 24th.
Just like we didn't with Ushuaia, in exactly the same way that we didn't in Ushuaia have to do this, we have to do this in the north. So refraction must have a proclivity to favor the south and have less influence on the sun in the south.
You can clearly see how the image of the sun begins to going down. So at what moment this, transition happened?
In that simple statement is the key to science. It doesn't make a difference how beautiful your guess is. It doesn't make a difference how smart you are who made the guess or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it.
Now, let's move to Caña Piscao. Remember, this is the geometry of the globe, and this absolutely proves. Now, let's go to here.
Going to look at the equinox geometry first. If we advance time, you can see the sun is now moving to the right as it sets. When the sun center crosses the horizon, the day before the equinox, you can see it is not at the west position.
Okay.
We have to move one day ahead to the 22nd. And as the sun center crosses the horizon, you can see that it is extremely close to directly west.
Yes, we really can see that. We can also see that the time in Cañapiscao is 3:32 p.m. Shall we check whether it's 3:32 p.m.? Now, 22nd that was. Okay, so let's go to the 22nd. Well, look at that, sorry. The sun doesn't set at that time. It sets like 3 hours later. Let's check SunCalc. Cañapiscao on the 22nd, and refraction or non-refraction. Yeah, sets at the same time as time and date. Now with refraction and without refraction, removing refraction, you're adding 4 minutes. That's all we're talking about, 4 minutes, not 3 hours, Wolfie.
Or what his name is, if it disagrees with experiment, it's wrong.
Wolfie, what the hell are you doing? You think the sun at the same latitude north as that of Ushuaia in the south sets at 3:30? In the south, it sets at 5:30 or 6:30. 5:30 because hour differences. 3:30, you think, is the local time when time and date says the sun is at 270? You big clown shoe. Look, SunCalc says it will be 6:30. Time and date say it will be 6:30. Your splendid globe equinox geometry says 3:33 p.m. What a gaff, dude. And we're going to carry on watching.
And this is precisely the discrepancy that Antonio has identified. In Ushuaia, the 270-degree sunset occurs on the 21st of September. In Cañapiscao, it occurs on the 24th of September.
Even though they should both mirror each other, because they're on the same longitude and the same distance away from the equator. They should literally mirror each other. The sun should be going left in one and right in the other. Not some time distortion, and your globe geometry can't show it accurately as we see here, because according to your globe geometry, time and date should be reporting that the sun with refraction sets at 3:33 and without refraction at 3:30 or 3:29.
It's wrong.
So there's the punchline, Antonio. You have just confirmed the globe.
Ooh, have I really? Or have I just shat on your breakfast?
The part I find most amusing every time a flat earther produces evidence in support of the globe is how many other flat earthers just blindly praise the video without obviously understanding what they are watching. Here are some examples.
Okay, so he didn't really bother checking the details properly, so he messed up. Despite not having checked the details properly and having seen what I showed, he still thinks that what I showed is proof of the globe. I've now shown that the globe equinox geometry is broken because in the real world, the sun will not set at 3:33 p.m. in Cañapiscao. Just absolutely proven it. The geometry of the globe is broken. And that, according to him, is still proof. You know, whatever it is, it's proof. Gyroscope not drifting, proof. Things too far, proof. Proof of the globe. It's all proof of the globe. Wow. What is wrong with these people? What is wrong with them? Oh, look. The sixth, well, no, not the sixth. The third. The third is 12 hours. Goodness gracious, that's 20 days away from the 23rd. Look, this is time and date again. See, Jakarta, When is it 12 hours of day and 12 hours of night? Well, about 20 days before the 90 east and 270 west thing.
As sure as the sun rises in the east and sets in the west. Stay curious.
As sure as the sun rises in the east and sets in the west.
So, I mean, this is kind of the issue is that, yes, if you're standing at this location right here and you're looking dead east, well, if you turn around, you're looking dead west. So to us, we think that it would look like a cross when you get far away from it. But if you really pull back, you'll see that that line is actually, and it's always a great circle. That's where these lines come from. They're all great circles, but it's certainly peculiar. It's not the way you would think. It is kind of counterintuitive. But I mean, people think that, you know, I know the big joke about the flat earth model is that if you circumnavigate the flat earth, that you're always turning your wheel. They'll just laugh at you and say, well, what do you mean? You would always be turning the wheel of your boat or of your plane. Well, it's the same thing on the globe. People think that if you started out this way, that you would, well, if you stayed straight, you would stay on this white line, and that you would go nowhere near where you think you're going. People think that if you go on this line, that that's a straight line. No, you'd be turning left. You'd always be turning left, because no matter where you're at, you know, take each of these crosses, east is this way, and then east is this way, and it constantly adjusts. If you just stayed east from your heading from where you started, you would coast down in part of the Great Circle, and you'd end up here like at this equator here. And then also, if you bring up like a spherical triangle, I mean, this is just another thing that they always use, right? So here's your triangle. They always talk about how the globe has a spherical triangle, meaning if you pull in here and you look, there's the 90-degree angle, and then you pull back, there's a 90-degree angle over here, these green lines. So you'll see again that that's a 90-degree angle at this green line. And so you have 90, 90, 90. So you've got your, you know, 270 triangle, which we know doesn't exist on a regular flat map, but that's the way they get away with it, because these lines are nowhere near parallel. You know, they both curve in, and again,
right, it's an oblate triangle, and so obviously the angles are going to meet. It's not as if we're dealing with straight lines,
right? Because of course that'd be impossible, right? If you did three 90-degree angles, or one here and one here, you would just end up with a unfinished box that would never connect, and that would be the definition of it. That if you have a 90-degree angle here and a 90-degree angle here, well, these lines can never meet. They would have to remain parallel to each other for forever. But because of the way the globe works, that they're angled down, and that's the thing about the flat earth that, you know, I think people don't understand, that it works the exact same way. You know, it just so happens that if we drew these 3 points on a flat earth map, that they just wouldn't make a spherical triangle, they would just make a regular triangle. And people would say, oh, but you're not making a 90-degree turn. Well, neither are these people here. Well, they technically, I guess you can. It depends how far you're talking about. Are you talking about if this person came down here and made a 90-degree turn and went this way? Sure, you made a 90-degree angle here, but you're actually walking back towards this angle here. You're not staying at that 90-degree angle, or else you'd be following this white line here. So it's just something that people don't understand. They think that when they say the sun rises to the east on the equinox for everybody, you know, and I can admit I was one too that thought that meant east for everybody. But if everybody's east is technically looking at the equator, then it makes tons of sense to me. Of course, that on the equator, on the equinox, the sun is above the equator. And if everybody's 90 degrees is looking at the equator, then of course the sun rises in the east for everyone. So, you know, it's just one of those things. It's the same thing that they have a problem with they keep going on and on about things rising south of east down in Australia or wherever. But again, if you were here, well, let's say we're at this line here, and you're wondering where the sun rises on, say, somewhere near their summer down here in the south, well, it's going to rise south of east. And it doesn't mean, you know, they're looking at it as this is east, this line that kind of tails off this way. So there's, you know, lots to do with this, with the globe, and the whole idea of it being a deception, that it's not, you know, we don't live on a globe. And just because they were able to put longitude and latitudes and give us our coordinates on the idea of a globe doesn't mean that's where you live. So that's,
well,
you know,
You know, the whole argument that you mentioned about if it, you know, on a flat Earth, you would have to, if you're going west, you would have to keep turning your car to the right or your nose of the plane to the right or whatever. I mean, we're dealing with such vast distances that it would be just minor course corrections anyway. But from what I gather, if you align your car to a really, really distant, say, cityscape that you can see that's 30 or 40 miles off in the distance where you can sort of freely travel and align it to where it's, say, like due west or due east of you, that it will start to slightly phase out of that alignment, which is sort of, you know, helpful, or it sort of aligns with the azimuthal equidistant sort of flat Earth map. But we're not talking about, you know, major course corrections where you're constantly turning right to go west or east. It's just very slight course corrections over long distances to where, you know, you wouldn't even notice it. And in fact, you know, as you're showing here, even such course corrections are necessary, assuming a ball. So, you know, it's
Absolutely.
a moot point either way.
It's exactly the same both ways. That's kind of the whole point of it, is that, yeah, if you just set out and you're just going directly east, then you're right. You would never even notice that you're making that kind of a turn. And that's part of the deception, is that people think, again, if you get down in here, that east is actually this white line here. So if you notice, and this is going across several states, or at least a state or two, but you notice that it just looks the exact same as this green line. As we head off this way, you'll even notice here, they look identical. So we've gone 5 or 6 states all the way to off to the coast, the East Coast. And we don't look like we've changed at all. But, you know, as you start going further, oops, that's the wrong white line. My bad. This white line up above here. So you'll see here, this white line and this green one are staying together. But then right here, they start to widen. And then you'll see that this would have been going. And Bob, you would know better because you fly. So that green line is what they call a heading, right? And then the white line would be like what they call a track. Is that the right names, or is there a different name for that?
No, that's actually very aptly named. Yes.
Okay. Yeah. So I mean, you know, when you put in your heading, it's like, you know, you're heading this direction, you're heading east, and the plane, you know, usually you do that through an autopilot, that it would keep on this track. And then if you are tracking a certain, and that's usually if you see a plane and it says it's going, you know, in this case it would be going, 90 degrees or 89. That's you're tracking that that direction. But heading and track are quite different because we just explained it. So anyway, it's
right.
just
Your heading is
your
heading is just basically your azimuth bearing, and of course that is corrected from the compass and also the magnetic declination, and then that's what you set your azimuth to on your plane, and then that's what you fly your heading from. So yeah, very good.
And I'll show this one more time just because I think it's important to know. But if we were up here in Denver where Bob is, and we track 90 degrees this way, so I'm going to put it at exactly 90. Okay, so right there. So that's 90 degrees. And if you were to take that spot that you went to and you were to track backwards west, that you would think that you go back where you came from. That would be pretty much what I would think everybody would agree with. But actually, if you grab that spot here, we'll make sure we get right on it, and you track back west, and so we're going to go to 270. 270, which you'd think would be right on this red line, is actually right there. Oh, that's 270.2 right there. 270 exactly. So that's what people need to understand, is that if this is dead east from this location, then you would think that this would be dead west from this location. But it's not.
That would make way too much sense.
Right. Yeah, that would be like reality or something. But no, this is kind of part of the deception that people need to see and explore and research, because in this lies the entire lie. You know, the entire deception is inside of this globe, and we can pick it apart and we can kind of figure out how they constructed the globe. And obviously that's why, you know, the Masonic symbology is the square and compass and the G and geometry, and it's all in their ability to trick you into thinking that you live on a ball, that you are stuck here, that there's no possibility of anything else. And that's how we were taught. So I can't hold it against anybody. I was taught the same way.
If you were to take the dead center of each of those lines, what would direct east and west be? So like the dead center of the red line, what would east and west be there?
So you mean like from right here?
Right here, like what would east and west look like?
90 degrees would be 90 degrees east is here. See, because it really angles up with this, this line here. And I always get confused. What is this? This is latitude.
Right.
So, that would be, but you know what? It's the same thing on the flat earth, John. Like really, if you got down real close to where this line is, that every single direction. So if you start here and went 90, then it would be here. And then if you started here, then it's going to keep going along this line. See, it's going to always stay, with that line. And that would be 90 east the whole time if I kept doing little lines. But if you're talking about a heading, meaning you start heading that direction, then your 90 east veers off that line. So it's kind of, this is what tells me that they took the flat earth and applied it to a globe. Because the flat earth, it's easier to describe the way it works when you think of the north being at the center and the fact that every step you take, your compass has to readjust to where the north is, which is going to kick. Let's say we're going east like this. So as we take one step, the north kind of turns a little bit, which is going to kick our east up towards the north, just a little hair. So every step you take, you're kicking that east up north. And that allows you to stay on that white line. But if you're talking about a heading, then you're just talking about pointing in that east direction and following that path. And in which case you would follow the red line, not staying upon the white line.
And technically, if you headed on a perfect latitude east path, you shouldn't have to adjust much if the Earth was a sphere. You really wouldn't. It would be more or less a perfectly straight line describing a great circle that went clear to the other side of the Earth. So
well, the only great circle is the equator, right? I mean, the only great circle going east-west is the equator. Every line going north-south is a great circle. Those are all great circles going north-south. So when you're talking about north-south, that's why we're only talking east-west here. North-south will never change. If they will always be on this line. Directly north will always be, directly north will always be on this line. And directly south will always be on that line. The problem is east-west, unless you're on the equator. The equator, east-west, is going to be exactly on that line. But as soon as you get off here, that's when they veer. Because to stay on this line, you would be heading north. Whereas to go east, your line's going to drop down because these aren't great circles. There's a name for them, but I forgot what it's called. It's like a semicircle. I don't know what it's called. There's a name that they call these lines because they're not great circles. So it's just, if somebody would think that if you were here and you went east, that you would just magically go around the globe. Well, you would as long as you're adjusting to north each step you take, because then you're going to kick east up to the north and you're going to keep
either way you'd have to make those sort of adjustments, especially far from the equator, in either model. And
you would never really notice it if you were close to the equator, which is why somebody here who sees the sunrise in the east on the equinox, of course it would just look exactly like they're heading to the east. But even somebody who's way up here who's looking at the sunrise on the equinox wouldn't notice, because when you get down and get real down here, well, east is going to look this way. So to them, it is looking towards the east. But really, when you look at the heading, it's going to be a line that drastically cuts all the way down and hits the equator at the, down here. So that's how they've gotten away with the whole idea of the equinox and the sun rising at 90 degrees for everybody, because we all thought 90 degrees is, anywhere you're at, you just draw a cross. And 90 degrees is this way. Well, that's true, but remember how far away the sun is to be rising above the horizon. That's really the direction that you're looking.
Stay curious. The equinox probably isn't what you think it is.
The hyperbolic paraboloid shape of the sun analemma is not just a path over a year time span. But that same motion is found in the sun's 24-hour cycle. This drift pattern becomes obvious when you track the sun with high-end trackers like Los Mondi trackers, and just track the azimuth of the sun and do not use the correction adjustments of the tracker so that it runs on its nominal speed of 15 degrees an hour. The drift pattern is also equal and opposite on both sides of the equator, which means that this small 39.8 mile diameter sun is moving across the sky at various observed speeds north and south of the equator. After 2 years of research and modeling, we were stuck and couldn't make it work to model the sun or any object accurately. We started from scratch again. After looking at photos of crepuscular rays of the sun, which all flat earthers have seen a million times, we came to a revelation many, if not all, flatheads have overlooked. When you look at crepuscular rays piercing through clouds over a lake or plain, for example, the angles of the rays end up at the actual light source, which is just above the clouds in most cases. But we know the sun is not right above the clouds. We started wondering what someone would see looking back from the other side and if he or she would see the same thing. Imagine a scenario where you see these rays over a lake. Those rays are lighting up a spot on the water. Now put another observer right across the lake looking back at you. Can he see those rays in that lit up spot on the water like in this animation? Let's take that one step further and give the primary observer seeing the rays a long pole with a mirror attached at the end. If he were to reflect that ray hitting the water to the observer on the other side, would he then see a reflection of the sun in that mirror? Keep in mind the distance apart here is only 40 kilometers, and where the sun should be for the observer on the other side. To make these light angles in 3D software, you will need, like we used here, a local light source. But in reality, when you move to the other side of the lake and turn around to look back, you will have the sun at your back. Therefore making it impossible to see the rays in the first scenario or the reflection of the sun in the mirror. We have therefore come to the logical conclusion that those rays are personal for any observer, as someone looking back cannot see the same thing because of his position towards the sun. Now, if those rays are personal and cannot be seen by anyone else but the observer himself, that indicates that the sun is a personal or local objective projection. This can be verified by anyone by doing the opposite side crepuscular rays experiment, like in this animation, and see that someone looking back at someone seeing those rays cannot and will not see the same thing. A rainbow acts the same way as the sun, being that you can only see it at a specific angle, and you cannot walk around a rainbow as it will always move away from you. And you cannot see the opposite side of a rainbow. A rainbow is a source projection, and its source is the sun. Therefore, if the sun is also a source projection of an unknown source, we can start modeling the path of the sun for each observer on Earth. We did this by taking just one longitude, that being the 0 UTC meridian on Earth. And inputted the data from observations for azimuth and declination of the sun and traced the sun object for that location for a year for each 10th latitude north and south of the equator, and just let the data run its course for a year. But the model became so heavy with data and tiny hair-thin tracer lines that even with a super machine, we couldn't render the result. After some trial and error, we finally managed to get a clear view on the end result. And even with our sun being an equal distance to the observer, the shape and layout ended up in a torus field around the Earth. We still have to figure out how to do proper 3D vectoring to get all the observed speeds and changes in the motion of the sun, creating a more true shape. But it became very clear to us that based on Ken Wheeler's research into magnetic holography, that the sun we see is projected into the electromagnetic field in the sky. The objective sun follows the magnetic field lines that are unique for each location on Earth. So the real sun is a source coming from outside of the so-called firmament, which probably uses light polarization that is projected into the magnetic field and rendered through the atmosphere. It is no coincidence that all sun arcs combined create this torus-like field, and this is version 1.0. As soon as we find out how to use equal distance 3D vectoring and a formula on the angles in the data sheets from observations, we can then get a true shape in second-by-second motion in the field lines. This torus field is by no means a stationary field, as the sun moves north and south during the year. We animated this in what we call the cosmic breath of flat Earth, and this shows that by simply increasing the current in the field from the North Pole, you then push the field south, and by lowering the current, it flows back north again. It can also be pushed back and forth by an outside magnetic field from beyond the Antarctic, 90 degrees south latitude. The southern magnetic anomaly is also a moving anomaly, and who knows what more lies beyond the southern latitudes, all of which have influence on the field. From a creation standpoint, it must have a function as well. If we animate all sun positions over a year, the animation gives the impression of a wave going around the field like an outside source pushing and pulling on the field and projecting its image, that being the sun or moon, in it. We do not know yet what, where, and how this outside source is mechanically working, so to speak, but from an engineer's perspective, everything that works like a machine or clock must have a basic principle and laws of physics to discover its nature. We just have to figure out where to go from here and what experiments can be derived to either build on this or modify the basic concept. With this concept, we can boldly say we have created a working flat Earth model that can be held up to scrutiny, evaluation, testing, and experimenting to either verify or debunk certain aspects of this model. It is therefore with great honor and humility that we present this first and only working flat Earth model with an actual base in geometry, science, and observations. In the coming weeks, we will be releasing ground views of this model to show that current sun angles are dead on correct.
Mercury.